Welcome back, and thank you for watching my third video. So in this video, as you can see here, we are going to be discussing three derivatives, and I'm going to challenge you using some of these techniques that we have developed here to try solving for a fourth one. So as you can see up here, I have redefined the derivative, and I have also brought into play by the binomial theorem. So I'm going to very quickly just go over what this means. So if we have x plus b, b can be anything, any number. X plus b to the n is just 1. X plus b to the 1 is x plus b. So if you work through these rigorously, you can eventually find out that Pascal's triangle gives you the coefficients of these binomials. If you did squared, 1, 2, 1, 1, 3, 3, 1, and so on. Now, something also important to note is that for the second number, it's the value of n. So we'll be seeing this going into use for this proof. So here I'm going to show you the proof for x to the n. I want you to try to prove this as kind of a challenge. Prove it for x to the minus n. So let's write this out. So we want to find the derivative d of dx of x to the n. How are we going to do this? Okay, so by looking at the definition of the derivative, we have x, we're replacing x with x plus delta x. X plus delta x to the n minus f of x, which is x to the n, divided by delta x. Now, using the binomial theorem, we can come up with some expression. And the best thing is you really don't need the rest of these numbers because, hold on a second, limit as delta x approaches 0. You're not really going to need the rest of these numbers, because which you'll see in a little bit because of this delta x. But we'll look at this. So using the binomial theorem, the first term is always going to be x to the n. And the last term is always going to be delta x to the n. So this is here, this is minus x to the n divided by delta x. Okay, so the second term we can see is plus n. Here we have 2, so this is for n equals 2, this is x squared, this is x delta x, this is delta x squared. This is x cubed, x squared delta x delta x squared, and delta x cubed. So we can do this n times x to the n minus 1 times delta x plus, now let's just call these terms a, b, and so on, plus a x to the n minus 2 delta x squared plus so on. You can kind of get where we're going here. So this sum would also include x to the n minus 3 delta x cubed So b x to the n minus 3, c x to the n minus 4, delta x cubed, and so on. No, delta x to the 4th, sorry. So here we have the limit of delta x approaches 0. Okay, so we have x to the n, we can get rid of these. So we have limit as delta x approaches 0 of n to the x to the n times x to the, sorry about that, n times x to the n minus 1 delta x plus a x to the n minus 2 delta x squared. Let's just add one more term. Bx to the n minus 3 delta x cubed plus so on plus delta x to the n divided by delta x. Now we can factor out, all these terms have delta x's in them, so we can factor out delta x. So we have limit as delta x approaches 0 of delta x times n times x to the n minus 1 plus a delta x x to the n minus 2 plus b delta x squared n to the x to the n minus 3 plus plus delta x to the n minus 1. Sorry if my TV gets in the way. So we divide by delta x. We can get rid of these delta x's just like we did in the first video. And we end up, and we can get rid of these delta x's as well. This becomes 0, this becomes 0, this becomes 0, and all these delta x's become 0. So we end up with just one term, n x n minus 1. So this is d dx of x to the n. And this is going to be our definition. This is going to be what we're going to be using when we're differentiating any term x to the n. So what I want you to try to do is prove this for x to the minus n. So our next example, we want to find d dx of 1 over x, so we can kind of use this for this, but I want to just prove using some of this logic. So using f of x plus delta x, 1 over x plus delta x minus 1 over x divided by delta x. And once again, we have limit as delta x approaches 0 of this. So what we need to do with this is find the find like terms basically. So we want to do cross multiplication. So we have limit as delta x approaches 0. So we're going to do cross multiplication here. X minus x plus delta x divided by x times x plus delta x. Okay, so we can get rid of this, and we end up with negative delta x divided by what's on the bottom, x times x plus delta x, and we have limit as delta x approaches 0. Oh, and I forgot the delta x. I knew I was forgetting something. So we're dividing this entire thing, and the entire fraction is, you're taking the limit of that. So we can rewrite this as limit as delta x approaches 0 of negative delta x divided by delta x times x plus delta x. So we can get rid of this. And we have limit as delta x approaches 0 of minus 1 over x times x plus delta x. Now here, we can just get rid of this delta x. We can turn this into 0. Equals negative 1 over x squared. So that's our derivative of 1 over x. So one last derivative that we're going to be doing in this kind of rigorous fashion is the derivative of sine of x. So we have sine of x plus delta x minus sine of x divided by delta x, and we have the limit as delta x approaches 0. Now, from trigonometry, we need to remember that we have an identity for this, such that sine of x plus delta x equals the sine of x cosine delta x plus sine of delta x cosine of x. So we can use this as our identity, and when we're finding the limit, so let's find our limit. So let's plug this into here. So we have sine of x cosine delta x plus sine of delta x cosine x, and we're taking the limit as x approaches 0 divided by delta x. Now let's separate these terms. So instead of rewriting it, let's just do this twice. Divided by delta x, and let's just not rewrite the limit term. So here we can kind of we can see. Okay, so the cosine of the cosine of 0 is 1. But we have the cosine of delta x divided by delta x. That's not an identity, that's just 0. And you can prove this simply by looking at the graph. So this is just 0. You can look at the graph of cosine of x divided by x, and you'll see that. Here's the interesting part. Sine of x, so sine of delta x times cosine of x divided by delta x. If you can remember from the last time, we have, so now our term is limit as delta x approaches 0 of, let's put this in parentheses, sine of delta x divided by delta x cosine of x. Now if you can remember, from the squeeze rule that we talked about last time, sine of delta x divided by delta x, when limit of delta x is approaching 0, that's 1. So this becomes 1, such that the derivative of sine of x equals cosine of x. And you can use the same technique for any of the trigonometric functions. So I guess you can try that for cosine, finding the derivative of cosine x, or finding the derivative of tangent x, or any of the inverse sine, cosine, tangent. So as a challenge, I want you to try finding the derivative of e to the x. So if you are able to get, I'm just going to erase down here. If you can get d over dx e to the x is e to the x, then you're golden. And if you want to challenge yourself even more, try finding the derivative of e to the ax using the same technique, and you should be getting a e to the ax. So with that, I hope you enjoyed watching my third video on the second video on derivatives. I hope to see you guys next time. Next time we'll be basically formulating our rules of these derivatives, since you have a basic rigorous understanding of calculus. So I'm going to formulate all these rules, and then we're going to look at these derivatives in a little more detail, and even get into things like second derivatives. And besides that, thank you for watching. I will see you guys again soon. Take care.